Good morning, everybody. Oh, again, this is mine. Good morning. We are on the second day, and we have the pleasure to welcome the Professor Ramon Hanssen, coming from TU Delft. You may know him. He has been famous for interferometric work in SAR, remote sensing, and for sure, it will be a pleasure to listen to him about the basics of SAR. We know that you have a lot to learn in the SAR domain. And in the afternoon, you will have the pre-processing of the SAR imagery and the time series with Magdalena. Before I let you start, I would like to invite you, for those who have already their poster. The poster panel have been set up already, and there is a list of poster with your name and a number. As soon as you find your name and the number, you can display your poster at the right panel with the same number, okay? And you can do that at the coffee break or at the lunchtime. Everything should be ready by 4 o'clock this afternoon for the poster session, okay? I'm sure some of you have already the poster, some other will still have to pick it up, okay? Thank you very much. And therefore, I leave the floor to Ramon Hanssen for sharing his knowledge on the SAR.
Okay, thank you very much, Pierre. So good morning. My name is Ramon Hanssen, and I was asked this morning to give you a brief introduction on SAR, synthetic aperture radar. And before I do that, I would like to get a bit of feel of who you are. So could you kind of raise your hand? Have you worked with SAR before? If you do, can you raise your hand? Okay, that's quite a bit, yeah. Okay, so I can skip half my lecture. And how many of you did not work with radar or SAR before? Okay, okay, so that's about the other half. So one half of you can go to sleep. What I'm trying to do is give you a general introduction, and so for those of you who are familiar with it, then bear with me. I hope that I will give you some new stuff in the end, but it will be basics mostly this morning. And for the other ones, I'll hope that I get you started, and for the practical in the afternoon with Magdalena. So just to introduce myself, I'm a professor at TU Delft, Delft University of Technology, and I'm in my field is geodesy, so I'm into surveying and measuring, let's say, ground deformation, and I've specialized on SAR interferometry indeed. So SAR is, let's say, my basic tool to work with, and the real SAR has been around for a long time, and for me, let's say, the real great thing about SAR is that if you use it in an interferometric way, you can use it to measure this, let's say, millimeter level of motion on the ground from far away in space. So that is still very spectacular for me, and we're trying to push that further in our research. So, okay, let's get started. I thought we have a 2-hour slot here, and I assume I heard that there's a break after that, but usually if I would be in your shoes, I would not be able to be concentrated for 2 full hours. So my proposal is that we have maybe after 45 minutes or so, we have a short break, maybe 5 minutes or so. You kind of, stand up or do something, and then I hope that I can catch your concentration afterwards, right? And otherwise, I will see people nodding in the back of the room, and that's not good. That's the first thing. The second thing is, please interrupt me, right? So if I go too fast, or if you have questions, or if there is something, then please tell me, right? It's nicer if we have an interactive session than that I'm just kind of broadcasting. The thing of radar is that you're in the transmit and the receive mode, right? So I'm in the transmit mode, and I hope that there is something which comes back, and then I'm in the receive mode. Okay, that's a challenge to you. Okay, so let's get started. So the main things I would like to cover, I think, which are essential if you need to know something about SAR, is about the radar itself. What does the instrument do? What is the characteristics of it? And there is some physics involved if we are dealing with electromagnetic waves which propagate through space and then through the atmosphere and then on the ground, and something happens to them. But you can also look at it purely from a geometric point of view. If we look at the SAR image, there is a lot of geometry in there. And then from this radar going to the concept of synthetic aperture radar is a very special one. I would like to discuss that with you as well. So these are, let's say, the main topics I think that should be there in every kind of general SAR class. And then in the end, depending on time, I have a couple of applications where in Delft what we're working on with agriculture and let's say more towards the biosphere. Okay, so why do we use radar? This is the standard question everybody knows, right? So why do we use radar instead of optical? And if every textbook, the first line or the second line, you know, clouds, indeed, and day and night, right? So that's the obvious thing. So it's an active sensor. We don't need sunlight, and it has imaging properties, right? So the radar, you have to imagine that the difference between, there are several differences between optical and radar. One, of course, is the wavelength, because we have a longer wavelength, everything, let's say, between a centimeter and maybe a meter or so. That is, due to the wavelength, we can penetrate the clouds and go through the canopy of trees. But there is one very big other difference between optical and radar. Does anybody know? If you look at the imaging properties. So wavelength is one. It's an active instrument. Say again? Sorry, I'm a little... Side looking, yeah, indeed. Good, that's indeed also, that's true. But there is one big difference which you don't read that much in textbooks, and that is if you compare it to optical, it's actually very obvious, but we're measuring distances instead of angles, right? What you're doing with your eyes now is you're measuring angles. My right hand and my left hand are for you in your retina in different locations, and that is because it has an angular difference, right? If I would hold my hands for you there in this distance and I would shift it a little bit, it would be hard to distinguish, right? Because you're measuring angles. Distances are different. In radar, it's the opposite way, right? So a radar is not able to discriminate angles. It only can measure distance. So that means that whereas an optical image is immediately imaging, because we have all these angles with our eyes or with a photo camera, with a radar, this is not so obvious. If you need to make an image of a radar, you need to do data processing. And this is not straightforward. Okay, the longer wavelength already indicated. And so there are different physical properties in the interaction of these waves with the ground and with the medium that it goes through. Now here is the standard picture, right? Here we have all the wavelengths starting from 1 Hertz in the upper left to 10 to the power of 20 Hertz in the upper right. And then in that whole region there is the visible domain. Let's see if we can... I don't have a pointer here. Well, this small thing here, that's the visible domain. It's only a very small part. And then we have the radio waves and the microwaves, which are covering a much bigger part of the spectrum. Particularly between 10 to the power of 8 and 10 to the power of 11. So 10 to the power of 9 is gigahertz, right? So we're at 0.1 gigahertz and let's say 100 gigahertz. This is the range where radar takes place. And in the past, when radar was developed, you know, it was usually around the Second World War, a little bit earlier maybe, and because of the military applications of it, people started to give them names, these different bands. So you had the I band and the G band, the P band, the L band. And these names do not make any sense, they were just codes. But one thing that I always tell students who start with radar is that this is something that you need to know by heart. You need to understand basically 3 bands, so the L band, the C band, and the X band. That is something you need to memorize. There's no way around it. So X band is 3 centimeters, C band is 5 centimeters, and L band is about 24 centimeters. And if you're talking to somebody in the radar domain, or if you're talking with other experts, or if you are the expert who's asked for questions, for information, you simply need to know, right? If you don't know these bands, then you cannot have a good conversation about the topic. So please memorize this. Okay, so basically if we're talking about radar, it's all the ranges that we can either indicate with our fingers, let's say a centimeter or even less, to our arms, right? Let's say a couple of meters, 2 meters maximum. Okay, why is this interesting? Well, that's because of the transmission through the atmosphere. In this graph, you see wavelength on the horizontal axis, going from very short wavelengths here in the 0.3 micrometers to very long wavelength. I think the upper right there is in centimeters, 80 centimeters. And on the vertical axis, you see the transmission through the atmosphere. So if it's 100, that means that a wave can penetrate very easily through the atmosphere. If it is 0, then a wave with that frequency cannot penetrate it. And here you see that the atmosphere has these different bands. Also in the optical domain, you know this because we're also using that. And some of the radiation that comes from space is blocked by the atmosphere. Fortunately, because there's also the ozone and the ultraviolet waves which are harmful for us. Now, the thing that we are interested in is the X band, the C band, and the L band. Oh, sorry. And what you see here is that these 3 bands are all, let's say, in this 100% transmission window. So this is also convenient. So it always works, and the atmosphere does not shield us. Okay. So there we go. These are the 3 bands. Okay, so then some other basic concepts. I will go through these basic concepts first, and then we go to the technology. So bistatic and monostatic. If you have an optical instrument, that is usually a passive instrument. So you have sunlight, which is the source. It reflects on the ground or on the atmosphere, and then the reflection is received by the camera or the instrument. Here we need to transmit, and we can do 2 things. Either we can have the same sensor which both transmits the signal and also receives the reflection. If you have such a radar, then you need to have a certain transmission window, send out the pulse, wait until it comes back, and then you have to kind of stop transmitting and start listening to the echo, right? So you have a radar which needs to flip continuously between transmitting and receiving. So that also means that you already need to know a little bit how far the Earth is away from you, right? Because if you mess up the transmission and the receive interval, you cannot receive something while you're transmitting. One way to circumvent that is using a bistatic mode, where we have one radar which could be, in the ideal case, only transmitting, and then you have another radar which is receiving, so it can only listen. There are several missions which are now studied by ESA also. One is called Harmony, and that is one of these bistatic modes, where we have the Sentinel satellite as the main transmitter. So that is the heavy, very expensive satellite that needs a lot of power, big solar panels, because it needs to transmit the radar waves. And then the idea is to have 2 little satellites which are only in the receive mode. And these are cheap. You can launch them at the same time. And then you get the situation like over here, where you have the red arrow is the transmission, and the blue is the reflection, which is then received by different satellites. I think that all the examples that I will show today are from the monostatic mode. So one satellite which is alternating between the transmission of a signal and the reception of the signal by the same instrument. Okay. And then I think this is the last concept that I would like to introduce, that is a continuous wave versus pulsed waves. So continuous waves are the ones that are used by the police to check you from driving too fast, right? It's based on Doppler. It's continuously transmitting something, and the change in the frequency of the reflected signal tells us whether an object is moving or not. And like I said, in actually all the Earth observation satellites that we have now, they're all pulsed radars. So they are sending away little pulses. It's like you're sending somebody signals with a flashlight. So you're sending away the pulse, it's reflected on something, it comes back, and then you receive the echo. Okay, now these are, let's say, the basic concepts that we talk about in radar, and then with these sensors and with these instruments, you can do many, many things. And here I put the list of all the applications of radar. And this is really, in a way, very spectacular, right? I will not go through everything of this. I think here the context of this class is mostly agriculture or forestry oriented. But there is so much you can do from this. And actually, all the time we're discovering new applications, new information content in that electromagnetic signal that we're getting back. And for me, this is really one of the most spectacular things of this instrument. That all the time there are new things that we learn from it. It's like looking at the world around us with different glasses. Okay, an example of a comparison, and I think for half of you this is already very well known, but this is an optical image of the catastrophe that we had with the, I think it was called the Prestige, one of the oil platforms in the Gulf of Mexico. What you see up here is New Orleans, the built-up area. This is the Mississippi River getting into the Gulf of Mexico. On the lower right, you see a big cloud field and the oil spill that we had. Oh, great. Thanks, Magdalena. Yeah.
This is for the presentation, but maybe just use the pointer.
Fantastic. Thanks. Yeah. This is the oil spill. This is New Orleans, Mississippi River, and the oil spill over here. Now, you see here, if the cloud cover would have been a little bit further, you wouldn't have seen it. This image was acquired by Meris, and Meris was an optical instrument on board of Envisat. And Envisat was one of the, maybe the only, but one of the few satellites which had both an optical instrument and a radar on board. So the radar was the SAR, and Meris was the optical instrument. So it was able to measure at the same time optical and radar. Now, this is the radar image that corresponds with it. Now, to appreciate, let's say, what we see in the radar image. So here we see the city of New Orleans. We see the Mississippi River. And this is now the oil spill that we see on the sea. Right, so let me ask you a question. So why do we see the oil spill? For those of you who are well known with SAR, you know. But maybe for those who don't, you can think about it. Yes?
Because the oil creates, let's say, it soothes the waves on the sea. It becomes flatter and flatter.
Exactly, right. Yeah, so the answer is that the waves, of course, there's a lot of waves here on the Gulf of Mexico on the sea. It's damped out, right? So the oil acts like a film, which kind of smoothes the waves. And because we have a side-looking instrument, like you indicated, it means that the signal goes from the satellite to the ground under an angle. And if it would be like a mirror, it would kind of reflect like a mirror, and everything would bounce back away into space, right? Because we're not looking down, then it would come back, but under an angle, it will simply disappear. Now, if the area is rough, then you get something back. And this is a nice image, if you're new to SAR, to get to know a little bit about what is happening, because you can learn a lot from this image. You can, for example, see also on which side the radar was flying, right? Was it flying on the left side, on the right side, low or upper? Let's ask you. Actually, it was left or right. So how many of you think it was flying on the right side? And how many of you think it was flying on the left side? And how many of you don't have a clue? That should be the rest, right? Okay, so it's interesting, yeah.
Well, the backscatter signal is stronger here on the right side, so it should be from the right side.
From the right side, indeed, yeah. And the way you can see, if you look at a radar image, is that you have this bright part over here and the dark part over here. And if you imagine this, it's actually intuitively not so difficult, because if we have a rough surface, think about the floor here, the carpet here, this is a little bit rough. If I would look at this from, let's say, a very steep angle, then the likelihood that it would bounce back away into space is higher than if I would look at it completely down, right? So the more I'm turning away from the nadir direction, so straight down, the less I will receive back. So in other words, this rough sea over here is bright in this case because the angle is steeper. It's also a little bit closer by, that also plays a role. But basically, this is the way that you can see which side the radar was looking at. So it was flying here on the right side and looking down. And because we know that all the satellites are right-looking, so if I'm the satellite, I'm flying in this direction, I'm looking always to the right side. It means that this was a descending orbit, so it's flying from the North Pole to the South Pole and looking at the image like this. Now, back to the oil. This smoothes it out, and this is why it is darker. We'll look at a couple of other images a little bit later. So now we already started with this geometry, the side-looking geometry. Let's look at a couple of more examples. So first of all, and this is, I think, for you, not a problem, but if I teach my student in Delft the first classes in remote sensing, and I ask them, how high is a satellite flying? They have no clue, right? And in fact, so the altitude is very low, right? So we have, for example, Sentinel here. is at 700 kilometers. Right? So I came from Delft here to here, which is maybe 250 kilometers. So if I would drive 3 times, I would already be at the altitude of the satellite. So actually it's very, very low if you compare it with the radius of the Earth. Here actually it's still exaggerated a little bit. It's even closer. And we're flying around the Earth while it is orbiting, of course. Now these distances here are expressed over here. So this is 800 kilometers, 1600 kilometers. This is about the range that the signal has to travel forth and back to from the satellite to the ground. Now, the descending and the ascending orbits ensure that we can cover the Earth with a certain repeat interval. And we have 2 names for this. One is the revisit interval, and the other one is the repeat interval. These are very distinct things. What you see here is the descending orbit when the satellite is flying from the North Pole to the South Pole. That is this one over here. And then we have an ascending orbit, for example, this one, where the satellite is flying from the South Pole to the North Pole. Now, the repeat interval is the interval that it takes for the satellite to circulate around the Earth, and the Earth is rotating beneath it. And after some time, the satellite will be above the same spot on Earth. Right? For Sentinel, this takes 12 days. Right? So you need 12 days. One orbit takes about 90 minutes, maybe 100 minutes. So that is very quickly. So during the time that we have this class, the satellite has made 1.5 revolutions around the Earth. Right? Now, the Earth rotates underneath it, and after 12 days, you kind of come back to the same track. So that means that this track here, this is a different satellite, but if it would be Sentinel, it would repeat itself every 12 days. Now, so that means that the revisit time, the repeat time is 12 days. For Sentinel, we have 2 satellites. That's very convenient. And that divides it by 2, so that means that the repeat time for the Sentinel mission is 6 days. However, if you look at a certain area on the ground, if we have, let's say, 1 square meter on the ground, then what you see is that we have both this ascending and descending orbit, which, of course, looks at the same square meter on the ground. So if I have for Sentinel every 6 days a repeat, it means that the revisit will be twice as much, 1 for ascending, 1 for descending, so that we get to 3 days. And now the last thing you need to remember is that if we design a satellite orbit, we do it obviously in such a way that the whole Earth is covered, right? We don't want to have gaps on the Earth. And on the equator, the Earth rotates the fastest. So that means that you design a satellite so that the equator, the images are really aligned next to each other. So 1, 2, 3, 4. However, it's like the meridians on Earth. If we go closer to the poles, that means that these orbits kind of overlap, right? And if we're at the poles, they would overlap maximally. Now, the satellite doesn't go exactly over the poles, but the overlap is maximum at high latitudes. And for example, where we are here, we're just southeast of Brussels. It means that these images overlap about 50%, right? So that means that the revisit time, which started with 12 days for 1 satellite, 6 days for 2 satellites, 3 days for ascending and descending, now gets back to, let's say, typically 1.5 days for overlapping tracks. So depending on where you are, if you're close to the equator, it's less. If you're higher up, it is more frequent. So this gives us a big opportunity to monitor all kinds of processes on land. So if you're mostly interested in agriculture, you could basically sample, theoretically, the Earth at a higher latitude every, let's say, a couple of days. The other thing that plays a role here is the fact that radar cannot be switched on all the time, right? Because it's a passive instrument. And we call this the duty cycle of a radar. So let's say that an orbit is, let's say, 100 minutes. So that is 100% of the time. And then the satellites that we're using now, for example, Sentinel can be used as a duty cycle of about 24 minutes around that number. So that means that we can transmit all these signals for 24 minutes, and then we have to charge the batteries. Solar panels have to get enough energy again to recharge the batteries to do it again. So a radar cannot be switched on all the time. And the shorter the wavelength, the shorter this duty cycle is. I think, from the top of my head, I think TerraSAR X, for example, as an X-band satellite, 3 centimeters, has a duty cycle of about maybe 5 minutes or somewhere between 5 and 10 minutes. So that means that you need to choose, right? You need to choose where do I switch the instrument on. And you will not have data at all locations. So if you're sitting here in the audience and you have one particular area of interest that you're interested in, the fact that I was telling you that we have this repeat interval and the revisit interval of the satellite doesn't mean that you always have the satellite data. It needs to be switched on. Now, for Sentinel-1, this is all, let's say, designed beforehand. So ESA has made decisions, and we didn't want, thousands of users calling ESA all the time to say, well, can you switch on the instrument for me? No, wait, I'm more important. That's how it was in the ERS time and the NVSat time. That is what really happened. And yeah, so sometimes you were lucky and sometimes not. With Sentinel, we have this kind of regular acquisitions. But if you get data from, for example, RadarSat, the commercial providers, or from TerraSAR or Cosmos SkyMed, for example, you can, call the agencies and try to get acquisitions, and you have to pay for it. Okay, so let's not dwell on this too much. So I cover this. So here we have the situation. The satellite is flying in the orbit. Antenna has a certain size. We're illuminating a swath on the ground. The range, or the slant range, is the direction here from the satellite to the ground. And the other direction is what we call azimuth. So that is the other thing. So if you're new to SAR, you need to remember the terms range and azimuth, because these are the coordinates of our image. So in a normal map, you have east and north. In a radar image, you have range and azimuth. One axis is range, the other axis is azimuth. So if you're communicating to a radar person, you do not only need to know what X-band, C-band, and L-band is, but you also need to know what range and azimuth is. Okay. Then if we look at this, and I already told you that we're measuring distances and not angles, that means that the world becomes distorted in a funny way. So if we're looking from the satellite to the ground, and we have 4 spots here on the ground which have an equal distance, so from A to B is the same length as from B to C, as from C to D, then measured from the satellite, it means that from A to B here is from A prime to B prime in the range direction, but B prime to C prime is much shorter, right, because of the elevation of the mountain. And C prime to D prime is even longer, also because of the elevation of the mountain. So we get a distortion in the image, visually at least, which depends on the angle, the slope of the mountain. If the mountain would be steeper, here we have this area is called foreshortening. If the area would be steeper, so suppose that the mountain would be as the red mountain over here. So now point B would be over here, but point C prime would be over here. So we have A prime, C prime, B prime, D prime. So the order would be reversed. So the funny thing is that the top of the mountain would be coming, we would see that earlier than the foot of the mountain. And I would like to make this little drawing because this is always something that is confusing if you're new to SAR. Let's do it here. So if we have, let's say, a building here, and we have an optical image. So let's say we have a camera over here, and the camera has a certain field of view. So I told you that the cameras and our eyes are measuring angles, right? So these angles here, these are all the same. Right? That is, let's say, the pixel size of your phone camera or whatever. So that means that in this image, if we have an image over here, then this spot here would be down here in the image, and this is the foot of the building over here. Here we would have, let's say, the windows, and I would see these windows because the building is falling away from me. So this is the roof. And here are the windows of the building, right? It's falling away from me. Now, if I look at the same thing with the radar, let's do this in orange. Now, radar is side-looking, but the radar has these kind of areas of same distance. So now, instead of the same angles, we have all these distances which are all equal. And now you see that for a radar image, if I would draw that over here, and I'm starting, for example, over here. So the foot of the mountain, the foot of the building is further away in the radar. It has this range here than the top of the mountain. So the top of the building. Sorry, I'm messing it up. So a roof of the building would be here, and it would be falling, let's say, towards me. Now, I cannot see the windows at the other side, of course, because it's in the shadow. So these windows I will not see. I will see some reflections. So suppose there would be balconies over here. I would get reflections from them, but they would be kind of laid over. And I would like to show you that effect in an image. But the basic thing is, because we're measuring distances instead of angles, we get this completely reversed image. And if you show somebody who doesn't know SAR, a SAR image in the first place, it looks like a black and white picture. So people, with your brains, you try to interpret it like a black and white picture, but it's not, right? It has completely different geometry. This is an example in Japan, so Mount Fuji. Again, here you can see the satellite was flying on the right-hand side of the picture. This side of the mountain is bright. The other side here is dark. And you can see it also here in the mountains over here. And there's a little bit of layover here, shadow in that region. Even more interesting, this is an area in China with an ALOS image, that's L-band data. And here, if you look at this long enough, you get completely confused, right? Because it looks like you're, seeing through it. And this is because of the layover. So this is a very mountainous area, and the tops of the mountains are closer to the radar than the foot of the mountain. So this is completely weird to interpret, and you need to really get some experience to see it. So again, it was flying on the right-hand side, but it is a lot of layover. Now, to make it even more clear, this is the Eiffel Tower, right? Here you see the picture, and again, now you have to fool your own brain, right? So my question again to you is, at which side was the sensor flying? Let's see, up or down? How many of you are for up? And how many of you are for up? Okay. How many of you are for the down? And how many of you do not know? It's a top, right? So this is what I think is a nice example, right? We're looking at this way from our brain, and for all of your life, your brains are used to see this, right? So we see the foot of the Eiffel Tower over here, so we're looking from below. However, this is not the case, because the top of the Eiffel Tower will be earlier in the image than the foot of the Eiffel Tower. So range starts here. This is close by the sensor, and here we're going further away from the sensor. This is first, this is later, right? So, and my last example is a picture that I use in Delft, because this is our campus area in Delft. We have a big building across the street from where I work. And this is like a ghost building, because you can see through it, right? Here, the building actually is over here, right? And so all these lines here are the lines of the building. And the fact that you can see through it is actually this effect, right? So we have a shadow area here, but at the front side of the building, there are objects which scatter as well. They have a small reflection as well. So the image is kind of overlain on something else. So this simply shows how tricky it is to interpret a radar image, right? You really need to stop yourself because your brains are usually fooling you. Okay, to finish this part, this is a favorite example because I could spend 10 minutes talking about this image. This is the San Francisco area, the Bay Area. We have the Golden Gate Bridge over here, which has a very bright scattering mechanism. It's a radar looks onto the steel of the bridge, goes to the waves and back, and there are many kinds of different reflections. Then we have the San Andreas Fault, right? The big fault which runs through California, which caused the 1907 earthquake in San Francisco, which is, I think, still one of the most dangerous faults on Earth because of the high populations in Los Angeles and San Francisco. We see the San Francisco airport here, which is very dark, and that is because here we have long wavelength. It's very smooth. The tarmac of the airfield is very smooth, so it acts like a mirror. And one interesting thing in downtown San Francisco here, this is downtown San Francisco, is this area where we have very, very bright scattering, right? And so the question is, what is causing that very, very bright scattering? Anybody have an idea?
Financial district.
Sorry?
Financial district.
The financial district, exactly, right, yeah. Here you see a picture, right? This bridge here is the bridge that you see over here with the pillars. And you see here that this part here has all these high-rise buildings, right, in the financial district. And here's another picture of it. So here we see this wig-shaped area over here. And simply because the area is more rough, higher buildings means more rough situation. That causes the higher degree of scattering. So the amplitude of our signal is very much dependent on this. Actually, there are three things which influence the amplitude. One is the roughness of the terrain. That's what you see over here. Second one is the slope. You also saw that, right? The slope of the mountain. If the mountain is facing the radar, you will get more reflection back than if the slope is further away from the radar. It's sloped away from the radar. And the third one is the dielectric constant. So let's say the degree to which properties reflect. And that is also interesting for agriculture, because the dielectric constant of an agricultural field is very much related to the soil moisture. Right? And if you want to use SAR for vegetation, you like to get away, the slope should not be interesting, the roughness should not be interesting, and then the changes that you see in scattering tell you something about the soil moisture, about the wetness, and crop yield, and it can be derived from that. So basically, the big trick, if you're using SAR, is that you need to decompose or to kind of unravel those three components. And part of it is easy, because the slope of a mountain will not change over time, right? The mountain will be there for the next image. But the other two are difficult. The roughness changes. For example, if a farmer plows his field, then the roughness changes and the backscatter changes. And due to the soil moisture, if the area gets wet, the dielectric constant changes, and that also causes the amplitude to change. So basically, these last two, that is always the big trick in using SAR for agriculture. Which part of the amplitude change is due to roughness change, and which part is due to soil moisture or dielectric constant.
Sorry, I have one question.
Yeah.
Why usually airport seems to be into the water of the bay? Why is it so difficult to distinguish the coastline? What is inland and what is water?
Right. Well, actually, here it's because the airport is in the water of the bay. So it's a good question, indeed. But so they made the airport indeed stretching into the bay. And it's just a little bit above the bay level. And what you see here is indeed I think the rubble of the stones, let's say, to keep the water out when it storms. Okay. So in the history of radar, this was all there were at the military first part, of course, and then people started to come up with all the civilian applications. And this is a beautiful image that I just wanted to show you. In the imaging of Venus. Right? Venus is covered with a very thick, dense atmosphere. And here you see for the whole planet the roughness changes, basically. Right? So you see the bright areas, which are like mountain ranges, they scatter more. And so by covering the entire planet with the SAR in I think the late 1980s, with the Magellan mission, you get these kind of beautiful images from the cover of Venus. And if you now know that there are these three components, then you can start to interpret these kind of images, because the changes in roughness will cause a change in the scattering, the brightness of the image. Okay. Now, I promise you to go back to the radar principles, and we have to go to the SAR. And if we want to understand what a SAR does, we first need to know which part of the radar are really important. And there are two things which are really important, which is the size of the radar instrument and the wavelength. Now, the wavelength we already discussed, C-band, L-band, X-band, and nowadays, so the new NISAR mission, the US-Indian mission, and I think also some of the older Soviet and Chinese missions were S-band, but most of them now are the other three bands. That is the wavelength. The other thing is the size of the radar, and this is very typical. A lot of the antennas are either phased array antennas. They're like a flat plate, like the blackboard over here, also about this size. So what you can see over here, this is the antenna, and simply the length of the antenna makes a difference. And why does it do that? Well, that is because the length of the antenna determines the width of my beam. And there is one particular equation here which I also usually ask my students to memorize, which is delta is lambda over d. What this means, so lambda is the wavelength. So if it's 3 centimeters, this is, let's say, 0.03 meters. And d is the length of the antenna. So simply, if this blackboard would be the antenna, compare the picture over here, then this would be, what is it, maybe 8 meters or so. So this would be 8 meters. So I have 3 divided by 800. Let's say 900 is 1 divided by 300. Radians. So 1 divided by 300 radians is, in this case, if this blackboard would be a SAR antenna and it would be transmitting with X-band, that is the angle of my beam, indicated here in this picture. There's a little factor alpha in front of it, which has something to do with the antenna specifics, but it's around 1. So what does this mean? It means that if we have a radar far away in space, we can look at 1/300th of a radian. Now, a radian, there are 2 pi radians in 360 degrees, right? So that is 2 times pi, so 6.28 radians in 360. So let's say 6 divided by 360 is 1 over 60. So let's say 60 degrees would be 1 radian. So this would be maybe if I'm not mistaken, 1/5 of a degree. I always make mistakes when I do calculations on the blackboard, so check, but it's a very small angle. Right? So 1/5 of a degree. Well, the degree is very small. 1/5 is even smaller. So that means that the area that we're illuminating on the Earth is this small angle, but then times the difference, times the distance. Now here, this is the NVSAT. Here I use this as an example. This is as a dimension of 10 meters in one direction. And we can do the calculation here. So in this case, it's C-band, so 5 centimeters, 10 meter long antenna. So the beam angle would be 5 milliradians, which would be 0.3 degrees. So this makes sense, 0.2. However, 0.3 degrees means, so it looks like a very small angle, but if we're transmitting the beam, the pulse over 850 kilometers, we have to multiply this with 850,000 meters. So that means that the area that I'm illuminating on the ground, this angle that I'm illuminating on the ground is 4.2 kilometers wide. Right? So that means that if I would use the radar on board of NVSAT, which is a very expensive machine, right? So we launched it into space. Sentinel also, very, very expensive. I think Sentinel is like maybe 1 billion euros or so. But still we have a resolution of 4 kilometers. Right, so that is horrible. So this is why, let's say, these SAR radars do not work if you simply use them as a radar. Now, here in this picture you can see this footprint, right? So this is here 4 kilometers wide if we do the calculation that we just did. Now, because we're looking at the site, we have a swath which is for NVSAT 100 kilometers wide, but for Sentinel this would be 240 kilometers even, so it could be very, very wide. But the width of this footprint is very poor, right? An image with 4 kilometers looks very poor. This is what it would look like. This is a very nice image that is in a paper from Didier Mazonet and Kurt Feigl, where they looked at a bit of an area of the Ukraine. And this is what you would see if you would have 4 kilometers resolution. Now what you see is bright and dark areas, so that is good. You see some discrimination, but it's very, very fuzzy. Okay, so the trick of the SAR is that we build up this synthetic antenna size. So I told you the length of these antenna would be, let's say, 10 meters. But what I could do, let's see if I can demonstrate it somehow. Well, I'll demonstrate it with my hands. So if this would be 10 meters, and I would be kind of flying with my sensor in a certain direction, that means that for this pulse, my position would be here. For the next pulse, it would overlap. For the next pulse, it would overlap. So I can kind of stitch all these antenna positions to each other, like here on the picture, between position 1 and position 2. On the ground, a certain point, a certain resolution cell, let's say a reflector or an object or a guy, a person who is walking there, would be the red dot, and it would enter this beam at position 1. Now, the SAR is sending about maybe 2,000 pulses per second, and it is flying with a high speed. Anybody know how fast the satellite is flying at this altitude? How much? No, it's not that fast. Yeah. No, so if it would be 20,000, so the circumference of the Earth is 40,000 kilometers, right? So then it would be 2 seconds to go around. That would be really cool. No, it's about 7 kilometers per second. Then it's times 3.6, so that would be times 428,000. You're right. Meters per second. They crashed an aircraft or a spacecraft on Mars because of these conversion problems, right? Good point. Okay. 7 meters per second. So that means that if we have 2,000 pulses per second, that we would have, let's say, 3.5 meters motion per pulse. Okay, so if my antenna is 10 meters long, and my next pulse would be 1 over 2,000 of a second later, then we would be half an antenna width further. So in other words, we are kind of continuously overlapping with all these pulses. And the trick then is that we build up this synthetic antenna. And a more difficult word for an antenna is the aperture. Right? So SAR, synthetic aperture radar, is nothing else than a synthetic, an artificial antenna that is very, very long. Now, if you would do that, and you would go back a couple of slides here. Let me see. Over here, yeah, so for lambda over d. So actually, if d would not be 10 meters, but it would be, let's say, 4 kilometers, if you would have a real radar with 4 kilometers length, you would be able to get this very high resolution on the ground. So that's the trick. That's how we do it. So by doing that, we can get from this picture to this picture. Right? We reduce the resolution with a factor of 1,000. In the other direction, in the range direction, we do something similar, but it's due to data processing and due to the bandwidth of the signal. But basically, the main thing of the SAR is that we can get from these kind of low resolution pictures to high resolution pictures using data processing. So I would like to, the remaining part of this lecture, I would like to cover a couple of things. I think I explained about the resolution in the azimuth direction, the synthetic aperture radar, which enables us to increase the resolution with a factor of 1,000. I also need to talk very briefly about the range resolution, how we can achieve it there. Then I would like to say a couple of words on scattering mechanisms, and then finally go to some applications that I was talking about in the beginning. Okay, so we said we have azimuth and range direction. Azimuth is known. Range. Let's look at the range direction right now. So we have the antenna in an orbit. It sends out a pulse under a certain angle, and that is scattered on the ground on a certain swath. And these pulses are repetitively sent away. So the red little blobs are pulses which are travel from the satellite to the ground. Now, if we have a pulsed radar, then what we can do is we can measure range. And basically the thing is that if I have a radar here at this side of the table, I have 4 of these bottles standing here, let's say these 3. Basically, I'm sending away the pulse. It's going to hit on the first bottle here, then it's coming back, and I clock the time, and that gives me my distance. Right? That is basically the thing. And the second bottle is a little bit further away, so the time will be a little bit further. Now the question is, if you talk about resolution, how far do these bottles have to be apart from each other to discriminate them, right? So we know that if these bottles would be here, I would not be able to discriminate them because they're at the same range, right? Now, if I would put them a little bit further away, and I would send my pulse, the pulse you have to remember is like I always see it like a flashlight. I have a flashlight, I switch it on, and then I wait a second, and I switch it off. Then my pulse has a length of 1 second, or 300,000 kilometers, right, with the velocity of light. So the discrimination of those two bottles, so at which distance I will see them as separate objects, is related to this pulse length. And what I did is I made a little animation of that here. So first of all, let's look at the physics of it. So we have, in time, we send away a pulse here. It has to have a certain amount of energy because it has to travel all the way through space. And we lose a lot of power on our way there. And at some point, it will hit the bottle in this example, or the Earth if we're in a satellite from space, and we get something back, which is the echo. Now, if you look at the differences in power, what you send away is in the order of 1,000 watts, and what you get back is in the order of nanowatts, 10 to the minus 9. So there's a big difference between what you send away and what you get back. And this is also why these radars are so expensive, because with the same antenna, you need to be able to kind of shout very, very loud by sending something away and listen very, very carefully to a very small echo. Now, what could also be is that while you're sending the pulses, if the object is further away, then maybe this reflection may correspond to this transmitted pulse. Right? So this is what we call the range ambiguity here. So this distance between sending away and receiving the pulse. But at some points we know. Now we know the pulse repetition frequency. So how many pulses per second do we send out? I just gave you the number, like say 2,000 here. This is for one particular satellite, 1,680 pulses per second. So that means that the period between every pulse is, in this case, 0.6 milliseconds. So from the leading edge of this pulse to the leading edge of this pulse is 0.6 milliseconds. I can multiply that with the velocity of light, and then I know the distance. Okay, let's switch these two. So here, this is an old slide, but the principle is still the same. The ERS satellite, it has a pulse length of 37 microseconds. Right? So my flashlight is switched on for 37 microseconds, and then it's switched off, and I get something back. So that means if I multiply it with the velocity of light, I get a distance of 11 kilometers. All right? 37 microseconds corresponds with 11 kilometers. So if these were the two bottles, the question now is how far do these bottles need to be apart if I have a pulse length of 37 microseconds? You could say 11 kilometers, because that is a distance, but let's do the computation. So the smallest distance between those two objects to be separated. The answer is half of this, 5 kilometers, because of the two-way travel. And I would like to demonstrate that here with the equivalent of the two bottles, which are the two green bars here, and here's my pulse. And if I toggle my PowerPoint here, you will see the pulse going towards the bottles in this case. So now we're here, now we're here. Now the first pulse will start to reflect, that's the red one. Now the pulse is still didn't reach the second one yet, but it is already reflecting on the first one. And here it will start reflecting on the second one, and so forth, right? So at this distance, now you see that we send out one pulse and we're getting two pulses back. And because the distance between these two objects, bottles or whatever it is more than half of the pulse length, the physical pulse length, now I can discriminate them. So if these bottles would be more than 5 kilometers apart, so closer than that distance, I would not be able to discriminate them. So now you see the similarity between what we discussed in the synthetic aperture case in azimuth, where we could not discriminate points if the beam was, let's say, what was it, 1/5 of a degree, then I had, let's say, 4 kilometers on the ground. I couldn't discriminate points within that pulse beam. And what I did is I used the synthetic aperture to get to a smaller beam. Now here I have a similar type of problem, because I cannot make that pulse length smaller. Let me go back. The 37 microseconds, if I go back to the previous slide, here. The 37 microseconds here is this time. Now if I would like to make it smaller. So suppose I would like to make it, I'm an engineer, a radar engineer at SAR, or I want to design a new satellite. I would like to make it smaller. So I would like to make it 10 times smaller. Then I go to 3.7 microseconds. That would give me immediately a resolution of not 5.5 kilometers, but let's say 500 meters, which is still horrible. But we like better. But the problem is that I need to have the same amount of energy that I transmit here. So within this, let's say the area that I have over here is the amount of energy that I need to transmit. If I make it 10 times smaller, the peak pulse needs to be much higher. And at some point, I reach my limits there. So I cannot make the pulse smaller and smaller and smaller while still emitting the same amount of energy. So this is a kind of physical limitation in our electronics and in our hardware that we have to deal with. So we need to find a trick. And we found a trick. And that trick is called the Chirp. Let me see here. And this is also usually my favorite slide of my lecture, because if I ask you to look at the left part here, you see time on the horizontal axis, and you see a waveform, right? And my question to you is, who of you is brave enough to whistle this signal? Yeah, all right, so do it to the microphone. So the satellite is constantly kind of transmitting a chirp, like the birds do, right? They chirp. And it's continuously doing that. And so you see that in the left figure here, so going from the low frequencies to the high frequencies over on the right-hand side. In the middle figure, you see that in a frequency graph, right? So we have a certain center frequency. Let me use my pointer. Center frequency here, this is 5.3 gigahertz, so this is C band, 5 centimeter wavelength. But here you see the bandwidth, right? So low frequency here means the low signal here, and this is the high part of the chirp. So this is what we call the bandwidth of the satellite, and this is also a thing that we often talk about. You know, if we have a new mission, and you have SAR or radar people talking together at coffee, they ask each other, okay, what is the bandwidth of your signal, or what is the bandwidth of your radar? So apparently this is some kind of magical thing. Now this has to do with this chirp. On the right figure, you see that the frequency here is on the vertical axis. So and this is time on the horizontal axis. So you go from low to high here over time. Now the trick here is that this, if I have the inverse of this bandwidth, I have something which I call the effective pulse interval. So the tau that I was just talking about, remember the pulse length, 37 microseconds, is actually 1 over the bandwidth. So if the bandwidth is 15 megahertz, this was the case for ERS, then 1 over 15 megahertz, so mega is 10 to the power of 6, so we get an equivalent of 64 times 10 to the minus 9 seconds, so 64 nanoseconds. So going from microseconds, 37 microseconds to 64 nanoseconds is a factor of 1,000 again, right? And then you can imagine that we do the equivalent thing as with the SAR, where we went a factor of 1,000 by increasing the synthetic antenna length, something like similar, looks a little bit similar like a bandwidth, just longer thing, to a longer bandwidth, which gives us effectively a shorter pulse length. So if we use this 64 nanoseconds over here, and I go back to my previous slide here, so 37 microseconds, 5.5 kilometers, that would mean that 37 nanoseconds, a factor of 1,000, would give me 5.5 meters. Now it's a little bit worse than that, so we're at 64, so a factor of 2 or something. So we're up to about 8 meters in range resolution. Right? So just for you to remember, if this is all new to you, the bandwidth tells me something about the resolution. So I get here to about 10 meter resolution for this sensor. Now Sentinel, this is an old slide, so Sentinel already made a big improvement. So the current SAR sensors, I think I have to do this by heart, I'm not really sure, but I think Sentinel is at least 4 meters or 5 meters in ground range. So So that should be maybe like 2 meters. So I think a factor 5 would be my guess. So I think we were getting up to, let's say, 80 megahertz bandwidth for Santino. Does anybody know by heart in the audience? I don't know by heart, but it's much more. And the current SAR satellites that are around, so with the TerraSAR X and the Cosmos SkyMets and the new satellites that are being developed right now, they go to 100 megahertz or 200 megahertz. So I think the maximum is now 25 centimeter resolution for a SAR. And well, you can do the math and compute what the bandwidth then is. So basically, this is how we get to the high resolution in range. So both in azimuth and in range, we have this about factor 1,000 improvement to get to the higher resolutions. Still, if you're from the optical domain, maybe you're used to much higher resolutions, especially for the commercial satellites. But if you look at, for example, Sentinel-2 or the Landsat or the SPOT data, it's about the same ballpark, right? We're in the order of maybe 10 meters or so. Okay, so that is, let's say, the thing that I think you should know about the SAR sensor and how we get the high resolution. Now, for the next part, I would like to kind of use the blackboard instead of the slides. Let's see if I can do that. Because I would like to tell you something about the scattering. This is also an interesting thing about SAR. So first of all, you need to think, okay, we're transmitting a wave, right? So something which is, let's say, 5 centimeters wavelength, coming from space to the ground. Now, if we have, let's say, a 10 by 10 meter resolution cell, we could argue that maybe this whole classroom would be one resolution cell, maybe 2. So my thought experiment is now, okay, let's assume that we are all in 1 pixel, right, 1 resolution cell. Let's take the roof off here, so the satellite will fly over, the pulse will come here, and it will start reflecting on all of us. So what is going to happen, right? What does the satellite actually get back? Now, what it gets back is a complex signal, right? You know that if we have waves, we can see that as a sinusoid, and the sinusoid has an amplitude, and it has a certain phase, because if I measure it somewhere in this axis, I have the phase, right? So 2 numbers. And these are basically the 2 numbers that I'm receiving from a SAR satellite, from the reflected pulse per resolution cell. And what I do is I denote that as a complex number. So basically, I have 2 axes. We call that the real axis and the imaginary axis. And one measurement for 1 pixel in a SAR image is a dot somewhere in this plane. So let's say maybe here. Now that dot could then therefore be explained with a real valued number and an imaginary number. If I have these 2 numbers, I know how to deal with it. Or I denote it with an amplitude and a phase. That would be then an arrow here. Right? So this arrow has a certain length, call it the amplitude, and it has a certain phase. So different from optical images, I have a complex number. So SAR data are complex data. For every pixel, you have 2 values. So that also means that if you get a SAR image, and maybe in the afternoon Magdalena will show you one, I'm pretty sure she will show you one. And if you would be able to open it, you will see funny numbers, right? Complex numbers. So now we need to kind of understand how this functions. What is the physics behind it? And then I like to go back to my example of this classroom. So suppose, let's start with a classroom which is completely empty. We take away all the chairs, we all move, we would just make it a flat, mirror-like surface. So then it would be something like the table over here. So let's assume that the whole classroom would be like this table. Now what would happen then is that if the table would be, or if the classroom would be very flat, we get this signal coming in, it's like a mirror, it bounces back into space, nothing comes back to the satellite, so I have 0, right? So the amplitude would be 0, I would get this here. So that is basically what happens also if you look at the smooth sea surface, for example. Then, nothing comes back, only the noise maybe of the signal itself. You get something, but it will be almost 0. Now we make one step, we still have this empty classroom, but we put a bottle there, right? We put one of these bottles in the middle of the classroom. And we have this wavelength of 5 centimeters, and the bottle is, well, maybe 20 centimeters or so. So there will be some kind of interaction, right? So the wave will come, satellite is over there, it will bounce on this single bottle, which is in this pixel. And there will be, you know, the electrons here will start to dance around, and there will be a reflection coming back to the radar. Okay, so what am I going to get? I'm going to get a weak response, right, because the bottle is small, so the amplitude here will also be small. And what will the phase be? Any idea? What will the phase be? Huh? A random number, yeah. So I don't know. That's the right answer. I have no clue what the phase will be. Why? Because this phase actually is dependent on the distance between the satellite and the bottle, right? So when I'm dealing with 5 centimeter wavelength, effectively that is, let's say, 2.5 centimeters, because I have two-way room. So 360 degrees of phase corresponds with half of the physical wavelength. Let's use the real number. So for C-band, so it's 56 millimeters, Sentinel. So the Sentinel data that you will work with. So half the physical wavelength is 28 millimeters. Sorry. This is equal to 360 degrees. Right? So this distance, this position of the arrow. So let's put this bottle away. I was talking about this one. So I will get an arbitrary value here. Maybe this one. Right? Now, if I would roll back time and I would kind of move my bottle this much, what would the phase do? It would rotate almost 180 degrees, right? Would be here, right? Because 360 degrees is 28 millimeters. I shifted it a couple of centimeters, maybe a centimeter or so. So this distance difference from the bottle to the satellite now has a huge effect on the phase. Okay? Now we put the second bottle there. Still we have the empty classroom, 2 bottles. Now I have, let's use a different color here. Let me make a new graph here. So this is the real axis. This is the imaginary axis. Now I have bottle 1, which was this one. Bottle 2 is at a different position. I don't know exactly where, but it is the same amplitude because it is the same size. Maybe it is this one. So, but this is still 1 pixel, right? And I cannot distinguish these two things if they're in 1 pixel, in 1 resolution cell. So what I need to do is I need to add them up. And I need to add them up coherently, as we call it in radar or in optics. So coherent summation. Coherent summation means that I can simply take this one, put it on top of this one here. So my resultant phase here, my resultant vector will be this one. So it will be longer than the previous one, and it will have a new phase. Okay, now we need to make the big step forward, because now we put everything in again. We put the the chairs and the tables and you and me, we're all in here now. And now you can look at each other and say, okay, we're all going to reflect, right? So this wave is going to reflect on all of us. So we're getting a whole load of kind of little vectors and big vectors and, you know, all these things together. And maybe there's one big object here, maybe the board or so, which has a long amplitude, and then the glass is a small amplitude, and all this stuff is getting together. So what I'm going to get for this particular pixel is the coherent summation of all these vectors, right? All these ones, I can add them all up. And in the end, all the reflections from this classroom together will be one resultant vector, which has one amplitude and one particular phase. That is going to be in my file, and that is what Magdalena is going to show you in the afternoon. Now, what is the consequence of this? So, first of all, let's do the other thought experiment. I'm sure that in this building there are more classrooms like this. Let's assume that there's another classroom at the other side of the wall where another class is taught now, and with the same amount of people, and the same guy is standing in front of you. What is the reflection going to be there? It's completely the same, right? Maybe even the same number of people. So what kind of value is the SAR pixel going to give next door if we have that one? Well, we take the roof off, same situation. Any idea? Would it be similar? Right? Maybe? Any other comments? Okay, let's go through it, right? So, indeed, there are several things which are equal. There are same kind of same people. There are all our twin brothers or sisters are sitting there, right? So the same jackets and whatever. But it will never be the case that they will be exactly at the same distance from the satellite, right? Because we cannot, sit still and make a copy of ourselves. There will be many differences, even though the objects are the same. So that means that these phases of each one of us, each reflection, will be completely arbitrary in another direction, right? Now, so we also get this kind of messy summation of all these vectors. But because of the fact that the phases are different, we don't necessarily get the same amplitude. Right? In fact, it could be, you could put all these vectors in such an angle that the summation does something like this. Right, like here. And maybe in the end we get almost no reflection back. Right? So this could be. It could also be that all these phases are coincidentally aligned and they are all like this. And all the vectors align like this. And I get a very huge reflection back. Now the fact that this is this kind of messy behavior, this is what we know as speckle. I'm sure you have heard the term before. So speckle means that if I'm looking at an homogeneous field, say I'm looking at a potato field or so, which is very, very wide, so I have many, many pixels on that potato field, and I would zoom into that potato field, in my amplitude will not have the same value at every location. So in an optical image, yes, optical waves are small, and the properties of the potato field are more or less the same, so we'll see a more or less homogeneous field. But if I zoom in a radar image, it can be that one pixel is much higher than the other. And I get this kind of grainy, pepper and salt-like picture that SAR is known of. So this is a very important part, right? The phase is even more unpredictable, right? It would be anything, right? So if you would be a very strong scatterer, you look like a very strong scatterer to me, you would be this one, right? And you would kind of fall asleep because my talk is boring. Your head would go a little bit back, and this would now go in this direction, right? So the phase would change considerably just because of the movement of one dominant scatterer. So if we now make an image, and I hope that Magdalena is able to show you this in the afternoon. So if you look at the radar image, we simply look at the amplitude here. We will recognize things. I showed you several amplitude images before the break, right, with the San Francisco and the mountains in China, whatever. So this is recognizable. This is okay. If I look at the phase of that same SAR image, it will be, every pixel will be different. If I would put a color bar next to it, it would vary between -pi and +pi, or between, let's say, 0 and 360 degrees, whatever these angles are. But it will be completely a messy picture. I will not be able to distinguish it. Now, this is also the trick for interferometry in the end. Is Pierre still here? Because I just, his laptop locked. So I'm not able to go back to my slides now because this is Pierre's laptop and he has his password is on there. So you have to either have to improvise or we need to find Pierre. Okay. So, but basically this is the problem, right? So if we, great, I'm getting out. So this is the problem, and because of this, the phase of a SAR image is not interpretable. Now, what we do if we use combinations of SAR, and that is what we call interferometry, is that we put one image on top of the other, right? And then I get a very interesting case, because although every pixel in that phase image is completely unpredictable and different from its neighbor, if I would make a new image under the same conditions, I would expect the same reflections, right? So the two pictures that I showed here for the two classrooms, this one and the one next door, if I simply freeze everything and we don't move, the satellite comes back again, we make a next picture, I would expect the same behavior. And if I do that and I subtract them from each other, I get 0. Right? That's the idea. So this shows you the very particular condition for doing interferometry in the end, because these images need to be the same. And now you know already, if you're working in agriculture, this is not going to happen, right? Because it is not so that we will freeze and we don't move, and then 6 days later the satellite will come again and we'll make the next picture. Everything will have changed, right? The crops will have grown, the fields are plowed, and many things will have changed. So this is why, in many cases, interferometry doesn't work, because things change. The nice thing of doing the interferometric applications, what I will show you in a minute, is that even though maybe for 99% of all the pixels that we have, this condition doesn't work, because things have changed in the meantime, that 1% of pixels will still be, if I have 1 billion pixels, 1% will still be, what is it, 1 billion, 10 million, right? So I still have 10 million measurements if I have only 1% of the data which are good. So, great, fantastic. Thank you very much. Yeah. Let me see. Okay. Okay, so that is my story about the scattering mechanism, right? So I hope that, is that clear? I'll move on with the other part, but does it make sense? Right, so the basic message is we have complex data. The amplitude is depending on the summation of all these scatterers within the resolution cell, which can be very arbitrary. It can differ from one pixel to the next pixel. This is giving us the problem of speckle. And we cannot zoom in to the pixel level like we can on, in the framework of an optical image. And the last thing is that the phase, so the second variable, let's say, in the image, is completely unpredictable. We cannot use it unless we use interferometry. Okay, so go flash forward here to the... Here we go. Very, very fast. I skipped a lot of slides, so somewhere here, remember this? Right, okay, so this is all, I'm going to skip all this. This is not so, not the main message. Here, this is what we discovered. Sentinel, maybe here. Lots of stuff. If you have time, if you like it, I can give you the full depth. Posting. This is basically goes back to what I just said, right? So this image that we have been looking at here, the image over here, is only the amplitude. And the complex data also has this other part there. So I'm not sure if you're used to work with complex data, but this is one notation for complex data. So an amplitude times the exponent of the imaginary number j times the psi, in this case, is the phase. So this is the phase, which is unpredictable. Okay, let me see. So this is a picture of the city of Delft in amplitude. This is a picture of Delft in the phase, right? Beautiful, huh? This is my city. This goes from minus pi to plus pi. So completely unpredictable, right? This is great, this is not. So the trick with interferometry is that we combine two of these images, and that is like magic, right? So if I would have a second image here and I would put it on top of it, then all of a sudden you would see all these beautiful patterns and fringes and really cool stuff. Okay, so a couple of words about TOPS. I already said this. This is my explanation of TOPS. So TOPS is a way of acquiring SAR data. So the standard way of acquiring SAR data is called strip map. And strip map is where if my head is the satellite and I'm looking to the right, I'm simply sending out pulses like this, right? So I'm kind of moving my beam like this over, that's also a chirp, right? Like this, and I'm illuminating the area like that. Now there are maybe 3 other ways how we can do this, because I told you that how long we can get a resolution cell in this beam determines the resolution, right? If we can get it into the beam longer, we get a higher resolution, basically. So what I could do is either I make the beam width wider. That would actually be good, because then the point over there would be in my beam. I have to be careful of the feedback until here, right? If my beam would be smaller, I would only have this point over a small period in time. So what I could do, if I would like to get maximum resolution, and that is what the military like to do, for example, if they would like to find tanks or objects, or they would like to have the highest resolution, they rotate the beam. So they say, I'm interested in something over there. So here's my satellite. I'm rotating the beam like this, and then I'm kind of moving all the way until here, right? Now I have a very long aperture. Long aperture means the SAR, the synthetic aperture, is very long, so I have a very high resolution. That is called spotlight. Now, what happened with Sentinel is that there was another approach, because we would like to have two things. So the spotlight is great if you're in the military and you would like to see if there's a tank in the forest, for example. But the problem is that you can only illuminate a very small area, right? Because while you're doing this, you cannot look at that area, right? So this is all very limited. So what we would like to do with Sentinel is to cover the entire Earth, that's one thing, and with the highest resolution possible. So what we came up with, and basically the colleagues in Politecnico Milano came up with that idea, is they rotated spotlight in the other way. And they did it in a very funny way. I think it's still hilarious, because they call it TOPS. And TOPS is the inverse of spot, right? TOPS, spot. And so then they had to find an acronym for it. And so they figured out the acronym, what it means, while they said, okay, we're going to turn it around. But the idea is that they use a kind of broom type. So again, let me demonstrate both of things, doing my little dance here in front of you. So the spotlight is doing this, right, here. So I'm illuminating the area for this whole time. TOPS is doing the other way around. I'm flying in that direction, but I'm kind of shifting like this. This is my little dance, right? So it's like if you're cleaning the kitchen and you're rooming, you're doing it like this, right? So you're kind of sweeping the floor like that. That is what TOPS does, and that is the trick how we get to this combination of a wide swath and a high resolution. So here you see how the different, let's say, sweeps cover the Earth. So here we are, the first sweep over here. And then we sweep that part, and then we sweep that part, and then we sweep this part again, and then that part, and that part. Right? During the coffee break, you can all do my dance, and we can do it together. Like, okay, so this is how it is working, right? So we're illuminating the whole area. So the great thing is we get the same resolution that we had before with Envisat, the predecessor of Sentinel. So the resolution is about 4 meters by 20 meters, but the swath, so the area that we can cover, is now, instead of 100 kilometers, is 240 kilometers. So much more swath. And basically that also means that we can have the revisit higher. So Envisat was every 35 days. So now we have every 12 days. And we have 2 satellites, so every 6 days. So this makes a big difference, right? So this is how it works. Well, I have a couple of other slides here, which I will skip on. This is all time frequency domain plots, but this is basically how Sentinel works. So if you're going to work with Magdalena in the afternoon, you probably need to choose which kind of burst and which kind of subswath you're going to use. The problem that we have now also in these practicals, that the data are getting bigger and bigger. So if you would like to do this big size, your computer resources are high, it takes long, you cannot do it, let's say, within the time frame of one afternoon. So I guess you're going to work with a subswath, Magdalena, right? And maybe a couple of bursts only. Okay, but this is the main concept. Okay, just to finish it off, I promise you I would like to tell you a bit about our research now in the peat lands and in the agricultural applications. And I would like to show you a couple of slides on this. Now, sorry that this is a little bit messy, but this is my country, so the Netherlands. You know the Netherlands, we are walking around in wooden shoes. We have windmills, we eat a lot of cheese, and we have this flat land, completely kind of boring flat land with cows, and because of the cows we have the cheese, and this is why. Now there's a big problem. I would like to convey this problem to you. It's kind of a bit of a secret, but don't tell anybody. But we'll have a big problem in the Netherlands. Now the problem is this: we have land which is already in large parts below the sea level. So we have the sea over here, and we have these famous dikes. Right, the dikes protect the country, and behind the dikes are these pastures, the grassy fields where the cows are going, and because it's a delta area, here we're at the confluence of the Rhine River, the Meuse River, and the Schelde River. There's a lot of deposits, organic deposits of the rivers. And peat is one of the most important of them. Peat is a type of material which consists of organic material, so rotten plants and rotten animals, and it's kind of deposited on top of each other. It's very fertile, so this is why it's a good soil for the grass. So, but because land is so low, what we do is we need to kind of pump the water out. This is what we have the windmills for, right? So over 600 years, we've been pumping the water out, and therefore the level in the canals goes down. And that means that we don't live in a swampy area, but we have dry feet, and the cows can go there and produce milk for our cheese. Now, the problem is that once the water level goes down, then there is a part of the organic material which is exposed to oxygen, right? And if it's exposed to oxygen, it will rot, basically. It will oxidize. And that means that it will move away. It will produce CO2. So it's a relatively large part of our CO2 exhaust, methane. But more importantly, the land is going down, right? Because if the material goes away, the land is going down. So we're stuck with the same problem again. And we have a great trick. We just pump more water out. And we're doing that again right here. So the water goes out, and therefore the land gets lower and lower and lower. So I think we have lost maybe 10 meters of land since the Middle Ages. So if the dikes wouldn't be there, the Netherlands wouldn't be there, right? So the Delft, where I live, would be flooded by the sea. Now, this is all okay because the Netherlands is a relatively wealthy country. We can make good dikes, and if the protection is okay, then we can handle it. We think, we hope. But the problem is that next to these peatlands, we also have these old historic cities. The city where I'm in, Delft, is built in the 1500s. Leiden, Haarlem, Utrecht, there are all these kind of cities which are in the western part of the country, which are centuries old, so they have old buildings. Now, if you lower the water level in the pastures, the water level under the cities also goes down. And that has an effect on the foundation of these buildings, right? Some of these buildings are built on wooden poles, right? If the water goes down, the poles will start to rot, and there will be a lot of damage on the buildings. So while we have been doing this for about 600 years now we're reaching a kind of tipping point, because now what you see is that more and more damage in the old cities will start to occur. Now, going back to my problem, so this is a big societal problem. We need to either change our landscape, so we will not be the country of the cows and the windmills and the cheese anymore, but we will be the country of the swamps, right? Or the Everglades, wetland type of area. That's possible, right? You could do that. So if you do that, so you stop pumping the water, then you save the old cities, but the landscape is going to change drastically. The other thing is, we would like to keep our landscape because it's very important for us. So we need to keep on lowering the groundwater level, but that means that we will have large damage to houses. And this is basically, the houses are owned by individuals. The state is not going to pay for it, so a lot of people are going to have damaged houses, and there will be a rebellion, I think, against the government. So it's a big issue. Now, the problem is, how do you measure it, right? So the problem in geodesy of measuring heights is usually dealt with leveling, right? So you have bolts, you hammer a bolt in a wall, you put a leveling rod on it, and a surveyor goes and measures the height of that bolt, and the surveyor comes back next year, repeats it, and if the bolt is lower, you will be able to measure it. And the problem is that in the grassy fields, like we have over here, like the picture, right, you can imagine that in these areas, there's no way to put a bolt somewhere because the bolt would already drown by itself. And if you would, if you don't have a bolt, you can put your leveling rod there. But if you come back next year, if a cow has just put his feet there, the height would already be changed. So it's very, very difficult to measure this. Really a problem. We tried it using laser altimetry, airborne laser altimetry. You could make height models there, but that doesn't get the accuracy we need. We need to get down to the, well, less than a centimeter or so. So it is, or you need to wait for a very long time. Now, what we did with SAR is we tried to get, let's say, subsidence over these kind of areas. And now, getting back to the picture that I just drawn, you can imagine how difficult it is, because the scattering mechanisms change, right? If the grass grows, all these little arrows that I put in these two diagrams there, they will change. So from one image to the next image, it changes too much, and then I lose coherence, and then interferometry doesn't work. I cannot measure height changes. Here you see the area that we have been looking at. So this picture is elevation. This is one of these airborne altimetry data sets, and I'm showing you this because it's kind of interesting. So these are cities here. This is The Hague. Here is the city of Rotterdam. Delft is over here, and this is all this pasture land that I was just showing you. And what you can see here are these little anomalies in the elevation. So you wouldn't see them if you look at a picture. If you look at a picture like this, it's just flat land. But if you look at these very slight changes in the elevation, you see there are little hills. And this is because this was a sea level area where the sea came in, it deposited sand, and the sea went back, and so the sand remained. And so what used to be creeks, so shallow areas where the sea went in and out and sand was deposited, now it becomes little mountains because the creeks are filled with sand, the rest is peat, so it kind of does something like this. So the peat goes away, the sand stays. And this is why we see this. Now, the consequence is now that if we look at the subsidence of this area, we expect much more subsidence here and here and here than here. If there are sandy soils, it will not subside that fast. So in this area, it's not only very difficult to measure something because of the techniques, but we also need to have a pretty high resolution because it differs from location to location. Now, I'd like to change a couple of things here. So the way we do it is using interferometry. So the satellite comes over, it illuminates the area. Here I have a certain pixel on the ground, let's say 10 by 10 meters. Then after, let's say, 6 days, the second satellite passes over. And now the pixel has gone down. And now this motion, the subsidence d, can be measured as a fraction of the wavelength. And I told you the wavelength was, I think we have 28 millimeters here, effectively. So if the ground goes down 28 millimeters, which is this much, I will have 360 degrees of phase angle. So if it goes down 1 centimeter, I would have, maybe 120 degrees difference. And this, therefore, can be measured very, very precisely. If I can measure 1/10 of a cycle, that is then 1/10 of 360 degrees, so 36 degrees, would also be 1/10 of 28 millimeters, would be 2.8 millimeters. Now I can measure maybe 1/20th or so of a cycle. So I'm getting to a precision of measuring less than a millimeter of height change from a satellite which is 700 kilometers away in space, right? So this is a very spectacular thing. So we do this, and we look at all kinds of points. We connect them together. We make arcs between them. We have a lot of computer power, and we see how one point moves relative to the other. So the picture here has time on the horizontal axis. On the vertical axis is the phase, and the yellow dots are the measurements. Look at time. So if one point moves relatively up relatively to the other, then I have the yellow dots like over here. So time on the horizontal axis, phase here, so it goes up and up and up. However, this is like the clock, which is the big hand of a clock which goes around. If I would not have the little hand of a clock, but only the big hand, and counting the minutes, and I would be locked in a dark room, I would not know what time it is, right? I would easily lose an hour because I only have the big hand. So I know that it's 5 after the whole hour, but I don't know what the whole hour is. And that is the problem that we have here as well. So what we measure actually is the yellow dots into this light blue band. And our trick is, how do we get from the yellow dots here in the light blue band to the yellow dots on the dark blue band? That's what we need to do. Now we did that for a lot of buildings and hard infrastructure. Here you see an area of about 200 kilometers in the north of the Netherlands. And here these little dots are points where there was a house maybe, and the house moved, in this case due to gas extraction at 3 kilometers depth. This is about 7 millimeters per year motion. So this works well, but here you can see that all these areas in between these dots, that is where the grassy field is, didn't work. And that is interesting for agriculture. Let me go here. So here you see the same thing. So over these urban areas where you have a lot of green dots, means that we can measure the velocity of those points very well. If it's green, it's almost 0 millimeter per year. There are single houses here along the roads, and this may be a little farm over here. And if I click on that point and I look what the farm is doing, then I see, okay, this farm is actually subsiding. It's going down over time, 2010, 2016, with a velocity of 8.5 millimeters per year. That's the red line over here. And it goes a little bit up and down. This is probably due to temperature. You know, in the summer, the building is a little bit warmer, it expands, and in the winter, it's colder, and the building shrinks. So really, these very small measurements we can measure. So that's really quite spectacular. But the problem is that we're not interested in the farm. We're interested in the ground next to the farm, and that's where we have nothing. Here, if you can look at it again, so we zoom in, you see that all the reflections in our standard way of doing interferometry over a long time always comes from these hard objects. Yep.
Just by curiosity, it looks like between 2012 and 2004 there was not much dispersion, but recent years.
This one?
Yeah, for example.
Yeah.
Between 2012 and 2004 there is not much dispersion of the measurement.
Here.
Yeah, for
Yeah.
example. And in recent years it's getting more
Right.
dispersed.
Yeah, good.
Idea of-
Well, good observation. So let's say I give you my cowardly answer and my brave answer, right? So the cowardly answer is I don't know, you know. So so I have 1 million measurements, right? And so it's a funny thing. It's a good question. I mean, also, it bothers me because so it is kind of impossible to know for every point what it is, right? I can try to go there, have a look, but you know, if I go there and I give you a great answer, you're satisfied, then somebody else will ask me about this little red dot over here, right? So that is the cowardly answer. But we can do more, right? So this is also part of our investigation. So one thing is, for example, what we see is changes due to warm and cold summers, right? So 2018 and 2019, which is not on this graph, but were very warm summers. We see a completely different behavior there. So we see much more motion at that location. So it could be local effects. It could also be here that there's more dispersion in the end because the farmer, you know, here, he started to park his car here after that. He made a little parking lot. I don't know, right? So a lot of things can change for one of these particular points. And so I turn it around, right? So what I know is that there's not so much variation over here, and there's much more variation over here. So something happened there, right? And if it would happen at many different locations in the image, then I can extract information from there. So what we're working on now is using machine learning and contextual information. So all, you know, we know the weather situation, we know the temperature, we know what kind of soil it is there. We may know something about how old the building is. So we're going to combine all that information together to make queries possible on like you're asking now. Okay, just to finish it off, because I would like to show you some of our results. So we're stacking all these images together, right? So sorry, this is in Dutch, but this is you know, we're getting a whole stack of images, and we can make combinations between all these images. So basically, well, hundreds of acquisitions. We combine them all together. So here we had 7,000 interferograms, so a lot of computer work, not so spectacular. We look at it from different angles, the ascending image, descending image, the overlap. We can, so we're looking at the same thing with redundancy. And then basically this is, let's say, the thing that I would like to show, if this would work. I hope so. Does it do something? It's not my computer, so I don't know exactly how to start the animation. Well, okay, this is basically what you're going to see in the end, right? So if the animation would run, you would see deformation. So the good part of the message here is now that in the urban areas it's white, it's relatively 0 millimeters per year. And now we see that if we kind of average, we do a couple of tricks, we combine all the Sentinel tricks together, we do get some information on the amount of subsidence and over the pastures of the land. Here you see, for example, in 2017, how much change that was. And what we learned from that, which is, we didn't publish it yet, but it is, I think, something that is very interesting, is that this motion is much bigger than we thought. So we thought that the subsidence would be about 1 centimeter per year, which it is in many cases, but over the seasons we see sometimes differences of more than 15 centimeters. So that means that during the dry season it really dries out and it goes down. And this has kind of agricultural application as well. Finally, for the dikes, I told you that these dikes are very important to keep the land dry. You see here the land is much lower than the water, so the dikes are very protective. So we also analyzed the reflections that we get from these dikes, and you can see them over here. Green is relatively stable, but if there are red dots, it means that these dikes are moving, that there is some kind of instability over there. We analyze this in detail. So for these measurements that we have here, we took soil profiles, so we know how much clay is there, how much peat is there, how much sand is there, what is the decomposition of all these points. And then we found something very interesting. That is this thing here. So this graph has on the horizontal axis time, and on the vertical axis in blue the average deformation. So the blue line tells me that from 2009, 2010, these are the seasons, right? Seasons going up and down. So you see that this dike goes from -5 to, let's say, +2, +3. So let's say 8 millimeters up and down every year. Right? And now, if you only look at the blue line, you could argue, okay, this may be some noise in the data and goes a little bit up and down. But what we put in red then is the excess rainfall. So we said, okay, what is the amount of precipitation? What is the temperature? And then we compute precipitation, evaporation, and try to make a link there. And if you express this as excess rainfall, then you get the red line over here. And you see the amazing amount of correlation between these two values. So where we previously thought that, let's say, these millimeters, 8 millimeter range, so maybe a standard deviation of maybe 2 millimeters, that would be noise in the data. We now know that we can measure much more. There's much more information in the data than we thought before. If you look at the differences between the red line and the blue line, you get to less than a millimeter. Right? So actually our measurements were even better than we thought before. We just didn't have a way to explain it. And for me, that is, let's say, the main message also that I would like to leave you with. So the SAR data is, in a way, it's complicated data. If you're used to it, it's all okay. For those of you who are from the optical domain, and this is new to you, and you're looking at the complex data and the vectors, and I can imagine that it some people find it a bit frightening, but it's great, right? If you're getting into it, there is so much information you can extract from it, and the interesting thing also is that the Earth is a very interesting place. So we have lots of things happening at different locations, and even if we have a technique which may not work for one location, it may work for the other, right? And so in all cases, there's maybe I'll finish with this. This is something which is close to my heart. It's a kind of discussion also on the political level. So what we try to do, if you develop from ESA all these sensors and you try to develop techniques and new products, is you try to develop something which is generic, right? Some method, algorithm, you can get the data in, you push it through this black box, and some beautiful picture comes out with information. And what we see more and more is that it doesn't work that way, and that is because one place on Earth is not the same as the other place on Earth. There are always differences, climatologically, soils, land use. There's so much difference. So it means that whereas we are used to get generic products. I navigated here on my phone, right? Trying to find the location. This works basically everywhere as long as you have the good data. Maybe not so good in this town, by the way. But this is generic. That would mean that you don't need experts anymore, right? So we all, if you are either working in this domain or you're planning to work in this domain, if you graduate from your PhD or whatever you're doing, if you have the Google Maps, there is no job for you, basically, because it's there, right? The thing here is, whereas some people claim that we simply should build black boxes where you put these data through and then it's generically interpretable for everybody, it's not the case. I'm really convinced of it. So we need experts. We need experts who can look at these data, who can interpret it, who know that the change in the SAR image can be due to different things and that there are multiple interpretations possible. And this depends on the context. And I think that our goal as experts in this field is to provide that context, to have the overview, how do the techniques work, what type of problem do we need to solve. And this is why we are important. So maybe that is a good way to conclude this. We are important. Thank you. Thank you very much. So everybody wants coffee, right? So if you have questions, please come to me. Thanks.